Section 12.1, temperature and thermal energy. We are continuing our tour of energy. Remember in Chapter 11 we really focused on potential and kinetic, and now in Chapter 12 we're really going to focus on heat, or the concept of heat and thermal energy. So when we talk about thermal energy and heat, thermal energy kind of is heat, but what makes objects hot? When something feels hot, why is it hot? Right, or when something is warmed up or heated, what properties make it occur that way? It's because the speed of the molecules in the object are increasing. So anytime something appears warm, the faster the molecules are moving, the hotter the object is going to feel, because it's going to have greater thermal energy. Right? How do solids get hot? Something to ponder. How do solids get hot? Well, molecules can do two things. They can rotate and they can vibrate. That's how they really start to move in solids. In liquids and gases, the molecules are free-flowing and are able to move around a lot more than they are in solids. And solids are kind of stuck in place. But in solids, what they're going to do is rotate or vibrate. That's kind of how sound. You ever tap on something and you hear the vibrations on the other side of their feel the vibrations on the other side? That's because the molecules are vibrating all the way down. So solids get hot by rotating and vibrating. All right. Temperature. What exactly is temperature? Well, temperature is the average kinetic energy of all the particles in a sample. Now, here's your million-dollar question. Does temperature depend on the amount of particles or the speed at which they're going? The amount of particles or the speed at which they're going? Well, thermal energy or heat is based on the speed of a molecule, so temperature is the same way. Temperature does not depend on how many molecules there are. It only depends on how fast they're moving. It doesn't matter on how many molecules I have. It just depends on how fast they're moving. So temperature is the average kinetic energy of particles in a sample. And when we talk about our thermal equilibrium, we are being really vocab heavy here as we go through. When we talk about our thermal equilibrium, it's when our rate or our flow between two objects is equal and at the same temperature. They've finally balanced out. We are going to be studying with calorimeters in this chapter, and for those of you who are in advanced chemistry, you've already worked with calorimeters, and in fact this entire chapter is going to be very familiar to you because we've studied chemical thermodynamics already. So equilibrium is in which both objects have equaled out and are at the same temperature. So essentially, I have a glass of liquid water. I put ice cubes in it. What's going to happen to those ice cubes over time? They're going to melt, but the temperature of that water is going to drop. And when it's equalized, the ice and the water, even though the ice is melted, that's kind of a poor example, are in thermal equilibrium. Continuing more about heat. Temperature. Temperature is how we measure heat and heat flow. Now, we in the United States, we have Fahrenheit. The metric system is Celsius. Scientists tend to use what temperature unit? Right. We use Kelvin. And the reason we use Kelvin is because Kelvin does not have a negative temperature value. The coldest possible temperature value on the Kelvin scale is 0. So that is absolute 0. That would be negative 273 Kelvin. Negative 273 Celsius, or negative 454 Fahrenheit. So how do you use that? Kelvin is equal to C plus 273. It shouldn't be equal. It should be Kelvin is equal to C plus 273. And when we talk about heat flow, let's touch on the first top bullet point up there. As most materials cool, they contract and expand. Cool when they contract when they cool, and they expand while they heated. What's the one anomaly to that? Water. Think about it. What happens to water when it cools? Ice. It expands. Why do you have ice heaves on lakes in the wintertime? So as materials cool, most typically they contract unless you're water or a few other random materials, and they expand while they're heated. And when we convert Kelvin, Kelvin is equal to C plus 273, Celsius plus 273. You will get all these readings in your temperature values, typically are given in Celsius. Heat flow is the transfer of energy between two objects. What are the three ways in which we can transfer thermal energy? This is a 9th grade science question. What are the three ways in which we can transfer energy, thermal energy? Two begin with a C, one begins with an R. Convection, conduction, and radiation. Now, what are those values? Conduction is the flow of heat between two solids. So an example, if I put a frying pan on the oven coils are on the stove top, the range coils are getting heat that's going straight into the pan. If I put my hand on the frying pan, that's conduction. Two solids. It's going to hurt a whole lot, but that's conduction. Convection is the flow of heat through a fluid. Now, remember, a fluid's anything that flows. So air is a fluid. So your oven heats convection style. That is continually rotating the heat from back to front, bottom to top. That's a convection type system is in your oven. Right. A hair dryer would also be convection type. I'm transferring heat through fluid, which would be air. Then we have radiation, which is the flow of heat through electromagnetic waves. The sun. The sun gives off heat. All right, we can tell that on a cold winter's day. Standing in the shade versus the sun, you can tell the temperature difference. That is radiation. In fact, weather has to do with all three of these actually quite well. We have radiation, convection, and conduction. So those are the three ways in which heat can transfer: conduction, convection, and radiation. When we talk about heat, we are going to talk about the physics of heat. And when we talk about the physics of heat, we have to talk about specific heat. And in specific heat, every single substance heats differently. So every single substance heats differently. Every single substance absorbs heat slower or faster than others. For example, what heats up faster, an iron pan or a bowl of water? So if you have what heats up faster, an iron pan or a bowl of water? Let's think about it real quick. How long does it take to boil water? A long time. How long does it take to heat up a pan? A minute. And that's an example of specific heat. Specific heat is the amount of energy that must be added to a kilogram of a material to raise the temperature 1 unit degree. So we're talking Celsius or Kelvin. What that means is objects heat differently. If I have a low specific heat, that means I absorb energy very quickly. If I have a high specific heat, that means it takes a lot of energy to raise my temperature 1 degree. Now, the values for specific heat are on page 318. You will not have to memorize these. These values are always given. But mass makes a huge transfer with heat. Mass makes a huge difference with heat transfer. Think about it. It's easier to boil 2 cups of water than it is 4 quarts. The reason is mass. The more mass I have, the more energy it takes. So when we talk about heat, we have an equation. Q equals M times C times change in T. Like I said to advanced chemistry students, you already know this equation. Q equals M times C times change in C. Q is equal to heat. Heat is measured in joules. M is mass. Mass is measured in kilograms or grams. C is specific heat. That's the table on page 318 that you will use. And T is a change in temperature. But remember, temperature has to be in Kelvin. Temperature has to be in Kelvin. Mass will be in kilograms. From chemistry, that's a little different. Usually the mass is in grams in chemistry, but in physics, it's typically we use kilograms. So if we apply this equation, Q equals M times C times change in T, it's going to help us how much heat is being absorbed per any substance. So we look at an example. A 5.10 kilogram cast iron skillet is heated on a stove from 295 Kelvin to 450 Kelvin. A, what type of heat transfer is occurring? B, how much heat had to be transferred to the iron skillet? A, what type of heat transfer is occurring? We have three choices: conduction, convection, or radiation. I have an iron skillet on a stove. I have a solid transmitting to a solid. The correct answer will be, conduction. Next up, B, how much heat had to be transferred to the iron skillet? We're looking for Q. Remember, Q is equal to M times C times change in T. We are given the M value. M is 5.10 kilograms. C, the specific heat. It is an iron skillet. So if we look on page 318 in our book, the specific heat of iron is 450. And likewise, our change in temperature. Our change in temperature, 450 or 295 to 450, is a difference of 155. What we can do is we can put these all together. We can take our mass, 5.10, times our specific heat, 450, times our temperature, 155. We multiply these together. We have 2 sig figs as our answer. And when we do that, our answer becomes 36,000 joules. So Q equals M times C times change in T. C is specific heat. How much energy does it require per a particular substance? In the next section, we'll kind of look forward to thermodynamics. How does heat flow between objects now that we are able to calculate heat?